This video is going to be a bit different to the others. What I'm going to tell you in this video, you won't have to answer exercises about it or exam questions about it, but I'm going to tell you a couple of different ways of thinking about proofs that maybe you might find helpful. And I'm also going to tell you a bit of the bigger picture stuff. So you've learned about a formal system for writing proofs, but it turns out there's many different formal systems for writing proofs, and some of them look very different from the one that you've seen. So the one that you've seen is part of a family of proof systems which are called natural deduction systems. So natural deduction systems are proof systems that are based on the idea of introduction and elimination rules. So there are other proof systems that work on totally different principles. Also, me and Connor have modified it a little bit because both of us were unhappy about the way that we had first been taught about proofs. And then the implementation in Ask is also extended with some quality of life features that you don't normally find in a proof system. So the proof system that you've seen has some special properties. So last term in CS106, you learned about truth tables, and then this term you've learned about proofs in CS103. Turns out that there's a very important relationship between proofs and truth tables. So we're going to call a formula provable if it's possible to find a proof of it. So that is, it's possible to find a proof that ends with the sequence that has that formula on the right and no hypotheses on the left. And then we say that the formula is true if every row of its truth table ends in a 1. So that means that the formula is true no matter how you choose the atomic formulas being true or false. So the first important property is called soundness. And soundness says that for any formula, if it's provable, then it's true. So if you can find a proof, then it's guaranteed that every row in its truth table ends with a 1. The other important property is called completeness, and it's the exact opposite of that. It says that if a formula is true, then it's provable. So if every row of the truth table ends in a 1, then it's guaranteed that it is possible to find a proof. So together, this means that the true formulas are exactly the same thing as the provable formulas. So you can prove only things that are true, and you can prove everything that's true. So one thing you could do with that, for example, is to detect trick questions. So if somebody asks you to prove a formula, maybe it turns out that there is no proof. But if there is no proof, then it is possible to find a row in the truth table with a 0 on the right. I should add, on this course, we are never going to give you a trick question like that, so you don't actually have to worry about that. Okay. And of course, the proof system that we've shown you is definitely not the only one that satisfies the soundness and completeness properties. There's lots and lots of very different proof systems that have the soundness and completeness properties. Okay, the last thing I want to tell you about is a totally different way of thinking about proofs that personally, for me, I find super helpful, which is that you can think about proofs as strategies for a sort of game. So say you have a formula, and then you play a game with two players, where one of the players is trying to prove that the formula is true, and the other one is trying to prove that it's false. So it's kind of like a debate. It's like an idealized mathematical debate without the shouting and name calling and stuff in real life debates in London. So we call these two players the verifier and the falsifier. So suppose you have a formula that looks like P or Q. So the verifier is trying to argue that either P is true or Q is true. So the verifier gets to choose whether we go into the P branch or the Q branch, and then play continues on that branch. On the other hand, if you have a formula that looks like P and Q, the falsifier is trying to argue that P and Q is false. So now the falsifier gets to choose whether they think P is false or Q is false. So the falsifier gets to choose which branch to go into. If you have a formula that looks like P implies Q, what happens is first the falsifier has to say a proof of P, and then after that, the verifier has to give them back a proof of Q. Okay, I'm skipping a lot of detail here, of course. I don't have time to tell you about all of this in detail, but the rules of this game really match up completely with the proof rules. It turns out that a proof is basically the same thing as a strategy for the verifier. So a strategy is a kind of program that tells the verifier how to win no matter what the falsifier does. So the verifier can win in every situation. Except it's not quite true. I told you a small lie. This actually matches all of the proof rules except for double negation elimination. So it turns out that if you have a formula like P or not P, where you need double negation elimination to prove it, there's actually no strategy for the verifier to win that game. Except that we can get double negation elimination if we change the rules of the game a little bit. So now we're going to give the verifier a special move that only they can use. The falsifier isn't allowed to do this special move. The verifier can, at any point during the game, change their mind about one of their earlier choices, and then they can take back their moves and backtrack to that point in the game and make a different choice. But crucially, they get to remember what happened on their first attempt. So if the falsifier revealed any secret knowledge, then the verifier gets to keep that knowledge. Okay, so this is a bit mysterious. So let me tell you how the verifier can win the game for P or not P by using this special move. So this is an OR formula. So the verifier gets to make the first move to choose whether we go into the P branch or the not P branch. And the strategy we're going to give the verifier is to always go into the not P branch. So the verifier is arguing that P or not P is true because not P is true. So now for not P, the verifier is basically saying that they can turn any proof of P into a proof of false. So the falsifier can either accept that and then the verifier wins, or the falsifier can say a proof of P and demand back a proof of false. So suppose that happens, suppose the falsifier actually says a proof of P. Now the verifier says, aha, I've tricked you. Now I'm going to backtrack to the beginning of the game where I had to choose between the P branch and the not P branch. But this time I'm going to go into the P branch. So now the verifier has to give a proof of P, but this time I have one because you just gave it to me. So the verifier wins. So if you look at the proof for P or not P that uses double negation elimination, the proof actually follows the same structure as this strategy. Okay, welcome to the end of the first topic. Well done, everyone. You've made it through the first 2 weeks. I haven't made it through the first 2 weeks yet because I'm recording these videos out of order. So next week, we're going to be looking at inductive data types and recursive functions.